Okay, so so this is where we left off. We said we have this hierarchical distribution where from the uninformative prior, we draw our parameters alpha and beta. This is what we call the hyper prior distribution. Excuse me, because the beta distribution is our prior distribution, and it is defined by the parameters alpha and beta. These are the two shape parameters that define this beta distribution, and it is from this beta distribution that we are drawing our individual players' batting average, secret batting average values, okay? And so the values, the Bernoulli will come, when you draw this, this defines a Bernoulli distribution, and the Bernoulli distribution produces the data that we observe, whether we got hits or misses, okay? So we are observing, you know, maybe the player has 10 at-bats, gets 4 hits or something, and from that we infer back, we try to infer back what that player's theta is, right? And so, the whole point of Bayesian stats is that we don't have a single value for theta. Even when we infer back what it is, it still comes from some probability distribution. In our case, the beta distribution. Okay. So if we have like 40 players, we're going to have 40 different theta values. Each player has a different kind of internal batting average, and then there's the two shape parameters. No wonder this isn't working. The two shape parameters. No, it's too loud. I think there's few enough people that I can just talk. The two shape parameters, alpha and beta, okay? And we are going to kind of, we do Gibbs sampling, and we partition this out into a whole bunch of univariate things, okay? So we've got kind of 40 Bernoulli things, okay? This is a Bernoulli probability. I guess this would be a kind of probability, the likelihood of getting this data for some particular value theta, okay? And so this is going to be a product of a whole bunch of likelihoods, okay? And then we have a whole bunch of prior distributions, right? Okay, so this is kind of where we left off. So I guess I'll snip this here, okay. All right, so so this is how our Gibbs sampler will work. At each iteration, we are going to draw, we're going to randomly sample some kind of value here, right? And so Give me a second here. Okay, so yeah, so this is what we have, and so if we kind of imagine what our posterior distribution looks like, we can kind of just we can simplify all of this, the posterior. We can just say that we've got some vector of thetas. Okay, so we're going to kind of, all of this can become the probability of kind of our matrix Y given the vector of theta values. Okay, and then and all of this stuff over here, actually, I'm sorry, this is our theta, which, no, I'm sorry, yeah, this is right. And then all of this stuff, okay, this is gonna, I'm gonna just kind of simplify this to say theta given our alpha and beta. Okay, so our posterior is going to be proportional to so we have it as this product, and then we have the prior distribution, alpha and beta. Okay. Okay. Oops. And right now we said this is going to be uninformative, a constant, so we can kind of just hide it away, right? We're just going to say it's proportional, just to kind of simplify everything, to y given theta, and then the probability of the vector theta given the shape parameters alpha and beta. Okay, so what we're going to do is the posterior distribution of theta. Okay. Each theta sub j value, right? So this is the batting average of player J. Okay, so the posterior distribution is going to be beta of alpha plus k sub j and beta plus n sub j minus k sub j, right? So where k sub j is equal to number of hits for player J, and n sub j is the number of at-bats for player J. Okay, and so the way the Gibbs sampler will work is, to do this for each player. Okay, so for j equals 1 to j equals 40, draw a random value, theta sub j, from this beta distribution, right? Okay, so you're going to draw this, okay, and so this will be kind of your current vector of values, and then we do a metropolis algorithm for the probability of alpha and beta given our vectors theta and our data y. Okay, we're going to say this is equal to the joint probability of everything divided by the marginal probability of this, okay, which will just be proportional to what we had earlier, y given theta, probability of theta given alpha and beta times the probability of alpha and beta. Okay, and so for the metropolis algorithm, okay, we're just going to say, because this is flat, okay, this will just come from some kind of probability distribution. Okay, this is a likelihood. We just kind of plug this in, and we can get kind of p move, right? So we will, right? So one is propose some coordinate alpha comma beta. I mean, you could also do this. Okay, so you propose a coordinate alpha and beta, and then you calculate p move, which is going to be the min of 1 comma, and then it's going to be p of the alpha beta proposed divided by p of alpha beta current, okay? And then accept or reject, right? Or I'll say move or don't move. All right. Okay, so what does this kind of look like in pseudocode, all right? So what we're going to do is we're going to kind of build up a, we want big samples. We'll say we want a lot of samples for all 42 parameters, right? Okay, so maybe I'll say, I don't know, a lot. We'll say like 10,000. Okay, so kind of I can keep track of all of my, keep track of all the sampled values. In a kind of 10,000 by 42 matrix. Is that okay? All right, and so what I'm going to do, it'll be the outer loop. So I guess my matrix will just call theta, all right, which is 10,000 by 42. And then we'll say for, I'm going to do row in 1 through 10,000. So we're going to do this for each row, and then for one iteration, we're going to kind of sample each value for that thing, right? So the Gibbs sampler, we're going to kind of sample each of our things. So we're going to do kind of for, I'm going to do column in, first I'm going to do 1 through 40, okay? We're going to just do the theta values, okay? And basically, we're going to just say, you're going to have to figure out what y sub j is. Y sub j will be kind of the sum of hits in y for player j. Okay, so I don't know what, I guess, you know, y is basically your matrix of hits and misses, right? Okay, so y will be the sum of the hits for player j, and then nj will be the sum of hits in y for, I'm sorry, the sum of, I guess, the kind of length of yj. Okay, we'll need, I guess, some initial values for alpha and beta. So I guess we can just start off with alpha 1 and beta equal to 1 or something, just some kind of arbitrary value. Okay, so we'll just start there, and then and we're going to just sample. So kind of our random theta. Our random theta will be, we're going to use r beta alpha plus yj. Oh, we want one of these things. And b plus nj minus yj. Okay, and we will go ahead and we do that, right? Okay, so so now we just need the last two values. Okay, we need to somehow produce a value for alpha and beta. Okay, so you know we're currently at alpha equal to 1, 1, and I don't know what we're going to propose, but basically we'll need to write something to propose a new value of alpha and beta. And alpha and beta, the shape parameters can be pretty much anything, but they cannot be negative. Okay, so you know, I'm currently, I don't know, maybe 1, 1 is not the best place to be. Maybe I should start off at 10, 10 or something. Okay, it doesn't matter, right? You just start somewhere. Okay, so you start somewhere, and then and you don't want the shape, whatever you do, you don't want it to be negative. Okay, so so we need some kind of function. We'll have propose be a function, and what we're going to plug in to the function will be kind of our A current and B current. Okay, I don't know what we're going to propose, right? So this can be whatever you want, right? Should we use a uniform or Gaussian? Doesn't really matter, okay? Okay, so I guess I can do like R multivariate norm. R, is it MVT norm? I don't know. Okay, so you're gonna propose something using A current and B current. You're gonna ask for one of these things, et cetera, et cetera, et cetera, okay? So this generates one new value, right? So we're gonna have A proposed, I guess this is a single vector, alpha AB proposed will be the result of basically our propose on A current and B current. And maybe I'll unpack this, and I'll have A proposed will be basically the first thing in AB proposed 1, and B proposed so you have to kind of unpack it like that, right? Because our proposed function will return a vector of 2 values. So we're going to unpack that into A proposed and B proposed. Okay, and then we need a way to kind of calculate what the probability is, or the likelihood is, right? And so we said on the previous slide, we said this thing, the posterior distribution of A and B, is going to be proportional to the y given all of the thetas, and the thetas, probability of the theta given all the alphas and betas, okay? So we'll need a way to kind of compute this thing, okay? I want to say this is a constant given alpha and beta. So actually, I don't even think we have to we don't even have to worry about this part, okay? So as far as I'm gonna, okay, and then we'll calculate p move is equal to the min of 1 comma, and then it's going to be we're going to have to do P of A propose, B propose, divided by P of A current, B current. Okay, all right, and I've run out of space here. But let me, I'm going to make a new slide for what P of A propose and B propose should be, right? So what is probability of A propose, comma, B propose? Or just, it's just A and B, really. And whether you plug in the propose or the current values depends on how it's written, right? So probability of A given B, okay? So this is the function. Okay, and so we said the probability of alpha and beta given our theta and our y is going to be proportional to the probability of y given all of our thetas, okay, and the probability of our thetas given our alphas and betas, and the probability of alpha and beta. Okay, so far we said this is a constant, okay, and this, once the thetas are determined, this is also a constant with respect to with respect to alpha and beta. Like changing alpha and beta will not affect this thing. Okay, so really we just need this. Okay, we only need this middle part. Okay, so we're going to say probability of alpha and beta given our thetas and our data y is just going to be proportional to the probability of our theta vector given alpha and beta, right? Okay, so this is going to be the product of a whole bunch of beta PDFs. Or, yeah. Okay, so we have, so basically it's going to be, you know, you've got theta 1, so you're going to have to do d beta, right, because this is the PDF part, d beta of theta 1 given kind of alpha plus k sub j and beta plus nj minus kj, okay, times d beta of theta 2 of alpha plus k sub j, beta plus n sub j minus k sub j, times dot, 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 all the way up to the 40th theta value, right? Does that kind of make sense? So we're calculating the likelihood of our vector of thetas if we change what the alpha and beta are. Okay, so it's the likelihood of our data given some new values of alpha. Okay, so whatever this is going to be the thing. So we would write P is going to be a function of A and B, and it's going to return basically the product of, oh, I don't know, can I even vectorize this? I'm not sure if I can vectorize this. We got a theta vector. I don't know, you might have to do some kind of loop or something. Okay, theta vector given, you know, the proposed A and, you know, basically A plus NJ or A plus KJ and all of that stuff. I'm going to just write dot, dot, dot here because I'm not quite sure how it should look. Okay. The problem with running all of these products here is that you can run into some floating point issues because the computer is not able to actually calculate really tiny values that are super close to 0. And so we might have to convert everything into log values. Okay, so that will so we might have to deal with the log probabilities instead. Okay, and so if we're dealing with log probabilities, okay, log probabilities to avoid floating point problems. Okay, so basically we're going to do basically the log of each d beta, et cetera, et cetera, et cetera. Okay, and it's going to be a sum. The sum of all of these things. Okay, so you'll get this really negative number. And then as far as do we accept, okay, so instead of u being less than p move, okay, it's going to be the log of u. Is it less than the log p move. So you're going to calculate log p move. Log p move is going to be equal to the log proposed minus the log current. Okay. And on the computer, we don't even have to do the min, because if the proposed thing is more likely than the current thing, this thing's going to be positive, right? And so the log of u, which is always negative, is going to be less than that anyway. What's going on? Okay, so let me all right, so I'm going to just do true thetas will be sequence from 0.2 to 0.35. Is it, how do I do output length? Length out. What are my values of true theta? Okay. Does that make it any easier to read? I'll just do by equals 0.0. Sequence. How many values of theta do I end up getting? 29. 36. 38. Okay. All right, we're just playing it. Okay, so these are going to be my true theta values, just to keep everything easy. Okay, so these are going to be, so I've got 40 people. These are going to be the true values, and I'm going to generate a whole bunch of data, right? So I'm going to say my Y matrix. How would I go about doing this? This will be an empty matrix. We're going to give it 40 rows and, I don't know, 200 columns or something. Okay, and then I'll just do for I in 1 through 40, take, we're going to say hits and misses will be R binom, and I want 40 things. No, I want 200 values. Each one is 1, and the probability is going to be equal to true theta I. Is that right? That looks right. Okay, and we're going to store this into the Y matrix row I. We're going to insert hits and misses. Okay, so I got this. Okay, so let's just do the sum of row 1. Oops. Okay, so 32 divided by 200. Okay, so his true batting average is 0.2, but he was batting only 0.16. That was the worst player, and the best player is the 40. Okay, and so 72 divided by 200. His batting average is 0.36, and his true batting average, true thetas, 0.36. Okay, so he's hit batting exactly at his batting average. Is that okay? So I made 40 players, and they all have different thetas, but they're all evenly spaced out. This is a silly thing, but we're going to do this, okay? And then we have a matrix, 40 rows, 200 hits, okay? And we're gonna do our kind of our Gibbs sampler, okay? Because this is what we have, and so I guess my results will be a large matrix. Maybe I want of nothing, and we're going to have, we'll say 10,000 rows, and the number of columns will be 42, okay? So this will be kind of our results. Each column will represent kind of a random sample of that one parameter. We've got 42 parameters. Each column is going to represent a random sample of 10,000 values for that thing. So double nested loops, right? So, okay, so for each row, in I guess I'll do sequence along n row, no, not sequence along, sequence length. That's a thing, right? Okay, sequence length. Okay, sequence length n row of results. Okay, so we're going to have that, and then for column in 1 through 40. All right. Okay, so first we're going to generate using R beta. Okay, so my current alphas, alpha is 10 and beta is 10. Okay, and we're going to generate one value from alpha plus, okay, so we need kj is going to be equal to the sum of the Y matrix row j. Okay, and then nj, in our case, is just going to be 200 for everybody. But it could be different, right? You could have had a matrix with some NAs and stuff like that. Okay, so we're going to go ahead and do alpha plus kj and beta plus nj minus kj. Okay, and this will be our random theta. Okay, and we'll go ahead and we'll store that in results row comma column. We're going to put in our random theta. Okay, so that part's good. And now we have to do the last part, right? Okay, so so I'm going to need a separate function as far as we go. So the Gibbs sampler is this, but then I need a proposal function for Metropolis, and then we're going to need a kind of a likelihood function for Metropolis. Okay, so to propose, propose will be a function of A and B, and we're going to just say RMVT is R. Will RMV norm work for me? All right, I think I have to library MVT norm, multivariate norm. And then is RMV norm? Okay, yeah, RMV norm. Okay, we want one thing where the mean is equal to A and B, and our sigma matrix, I think this will automatically just generate from that thing. So let me just try it. If I propose and I give it 10, 10, okay, that's good. Great. Okay, that's what I want. Okay, so we're going to go ahead and do that. So that's our proposal function. And then to evaluate the likelihood, right? So I'll call this P is going to be a function of A and B as well. Okay, now how do I do this? Okay, so we're going to do the log likelihood. The log likelihood will start off with 0, and we'll do for I in 1 through 40. This is a little bit terrible, but we're going to do, we need d beta of basically our kind of in our current row. Okay, so we would need to know which row we're in, okay? So we're going to take from our results, we're going to go to row, and we're going to do the column, row, column. So results, row, column are the current values of theta, right? So the ones that we just drew in this Gibbs sampler. So we're going to go through these things. We're taking each of these things, and we're going to say, what is the probability of getting that if we have the alpha plus kj and beta plus nj minus kj. Okay, I guess I also need to have these in here, okay? So the Y matrix for the current row, okay? So whatever, oh no, this has to go into here. The Y matrix for the current player, right? So some of this player's things in the Y matrix, and we're going to do this. This is our d beta. Okay, so this is the log probability. Is going to be, we're going to take the log of this thing, and then I'm going to take the log likelihood is going to be equal to the log likelihood plus this log probability that I just found. Okay, we're going to sum that up, and this is going to, it makes sense as I'm writing it. I'm not 100% sure if okay, and then so what we want to then do is we're going to get AB, we will propose using alpha current and beta current. Okay, oh, I'm way over my time here. Okay, so we're gonna propose that, and we're gonna unpack that. It's gonna be AB1 is this, and B is gonna be AB2, and then P move is gonna equal, this is my function, right? So I've got P of A, B, and the row divided by P of alpha current, beta current, and the row. Oh, and I have to actually, I'm going to take the difference. Alpha current, beta current, and the row. So this is actually going to be log of P move, and then we're going to say U is going to be R unif 1, and we're going to say if log of U is less than log P move, then alpha current gets overwritten by A, and beta current gets overwritten by B. And then at the end of that, we will take into results row comma 41, we'll throw in alpha current, and results row comma 42, we'll throw in beta current. Okay, all right, let's see if this works. Oh, all right, so I'm getting something here. unexpected this in if log, oh, somehow this closed this. Okay. J not found. Where's the J? Y matrix J. Oh, and what do I want? I want it for the column is really the player. Okay. Alpha. Oh, everything is oh, it's alpha current. Okay, and beta current. Okay. Argument is of length 0, log u. What is log p move? Integer 0. Okay, so what is my current value for row? Oh, it's not returning a value. Oh, that's stupid. Okay. Okay, so now it's running. Oh, and I'm so nervous. And I'm so sorry that we're over our time. Thank you guys for being troopers here. And I hope I didn't break it. Oh, and I didn't have something to check. Oh, but it ran. Okay. So let's see what our results. Let's look at the first column. That looks, this is our first player's thing. Okay. And let's look at our 40th player's things. Okay. So my starting values look like they're influencing the results quite a bit. Okay. So if we compare the first player's posterior distribution, he's centered around 0.3. And if I look at the last player's posterior distribution, he's centered around 0.45. Okay. Part of that, I think, is because my starting values for alpha and beta were 10, 10, which would put our distribution centered at 0.5. Okay. I probably should have started with some better things here. Let's. I'm just curious what our distribution for alpha could be. Okay, alpha could be anywhere from 0 to 800. Or 0 to 80, and beta could be anywhere from 0 to 100. Okay, so I need to actually correct something in that when I propose things for A and B, they can't be negative. Okay, so that would probably break some stuff here. But it does seem to, the results do seem to kind of align in that the posterior distribution for the first player, which the true value, and probably if I ran it longer and I fix a few of these things, the posterior distribution for the first player is centered at a lower number of around 0.3-ish versus the best player. Their posterior distribution is centered around 0.45-ish, okay? Which is a reflection of the data that we observed in their hits and misses and things like that, okay? But again, probably also skewed by the fact that my starting values for alpha and beta were off as well. Okay, we'll end there. Sorry for going over, and have a great Thanksgiving holiday. We'll see you guys on Monday.